Okay, so assalamu alaikum and good morning. Today we will continue talking about synchronization. Basically, in the previous class, we have introduced the idea of a lock, and we said we're going to have implementation, algorithmic implementation of the lock, right? So you have seen the kind of the framework that we will use to run different implementations of the lock, okay? So today we're going to talk about the very first attempt to implement a lock in an algorithmic way. The attempt is based on this idea, okay? Usually if you want to solve a problem, at the very beginning you try it at a smaller scale, and then if things working, then you try to generalize it, correct? So this is what's happening here as well, okay? At the very beginning, okay, the attempt tried to coordinate the access to a critical section, okay, by using a looking mechanism for what? Two threads. So we have two threads accessing what? Critical section, okay? And we want to see whether we can coordinate how they access by using the concept of a lock implemented in an algorithmic way. The attempt is based on having a variable, okay? This variable basically takes one of two values. These values are the tasks IDs of the threads. The task ID of the thread, right? So if I'm creating two threads, I expect that their IDs are 0 and 1. Yeah? Yes? The task that they're doing, 0 and 1. However, the thread ID is something else, right? We agreed on that, right? Okay. So now the idea here, I'm having a variable, I call it term, and if you see the definition of it there, the declaration statement, private volatile integer term. So it's an integer value holding the task ID. Initially either 0 or 1, because two workers. Okay. Why volatile? Have you seen this before? Volatile? Volatility means always retrieve the value for this variable from memory. Not from cache. From where? Memory. Okay? To make sure if one of the workers updated, you always get the latest update of it. Okay? Right. So initially, we're going to set the term to one of these two processes. Say process 0, okay, or thread 0 in this case, because we're implementing them as threads, right? Now, for a thread to enter a critical section, we'll be calling one of which method? Entering critical section, okay? And then, if the method returns, then the thread is granted to enter the critical section. Do you remember that? Yeah? So, just to remind you of it, okay, this is what we had as the code for the worker, okay? The worker continuously what? Executing code. Sometimes it has something to do with critical section, so we call it that's the critical section of the code. It's basically here a method that does the sleeping. It's a utility method, okay? A method in the utility class that does sleeping. Or the thread or the worker might do something else, which is basically what? Executing non-critical section. Okay, and we model the execution of non-critical section by what? By again calling a method which does sleeping for a random time. So that's a utility method. However, here executing critical section is something what has to be guarded, and we do that by using a locking mechanism. Before entering the critical section, we have to obtain the lock. Obtaining the lock is an implementation of a method in the lock itself. So mutex is an object of algorithm 1, say, in this case, right? Okay? And algorithm 1 must have two methods. Entering critical section to obtain the lock, and leaving critical section to what? To release the lock. So that's how the worker works in terms of the logic of it, right? So if we call this method of the lock, and the method returns, means the worker is granted to enter a critical section, will proceed from here, so will be entering critical section and holding the lock. During that time, no other thread is supposed to be able to what? To enter its critical section. Once the execution of the critical section for the thread who's holding the lock is finished, then that thread should release the critical section. Releasing the critical section logic is implemented in a method which is leaving critical section. This is again a method of what? Of the lock, right? Of what? The locks, which is mutex. And you see that all threads, they work with the same lock, right? It's a safe with one lock that we pass to all the threads. This is just to remind you. So now we go here, okay? So entering critical section, the logic of it, how does it work? It says that for a worker to be granted entering its critical section, then that worker has to check the value of turn and compare it with its ID. Compare it with its ID. They are equal, then you are granted to enter critical section. Okay? But if it's not equal, then the worker should be what? Should just suspend itself, right? Suspend itself. Suspending is done by calling a yield method. Yield. Okay, yield does what? The suspension of the calling thread. Okay? Okay. Now, if a worker called entering critical section and had been granted, then it will be executing its critical section. Once done, then that worker, we have seen in the code of the worker, must call what? Leaving critical section. And leaving critical section is releasing the lock. And in this implementation, what does it mean to release the lock? Change the ID, change the turn to be for the other worker, okay? For the other worker, because we only have two workers. So change it, if you are thread 0, change it to thread 1. Change the value of turn to 1. And if you are thread 1, change the value of turn to be what? 0. That can be done by basically setting turn to be equal 1 minus t. 1 minus t. So if t is 0, it becomes 1. If t is 1, it becomes 0. As easy as that. So it's you can think of it as a safe or a room, okay, that has a locking mechanism, okay, and unlocking, okay. Basically, what's on the door of that room or safe is an ID. So a thread arriving to that room to execute critical section, because now critical section is within the safe, right? Within the safe. The only way to execute it is to get access to the safe, okay? So now the entrance of that safe, the door of the room, okay, has an ID. If the ID matches with the worker, then the worker granted to enter, okay? And once the worker is in there, okay, no other worker can enter because turn is changed, okay? And then after that, later on, you have to change what? The turn on leaving to give opportunity for others to enter. Do you think this is, I mean, this will work for two threads? So let's say for two workers for the time being. To have this as a valid implementation, then three conditions must be satisfied. Do you remember? Mutual exclusion, progress, and bounded weight. Okay? Mutual exclusion says that there is only one worker active in its critical section at any given time. One or no, none. Okay? But not more than one. And in this implementation, okay, there is only one working in its critical section or none at any given time. Because if one is in its critical section, means turn is the ID of the what? Of the thread in its critical section. And who can change it? The only one who can change it is the worker itself who is in its critical section. So no one can enter the critical section. True? Yeah? Okay. Now what about progress? The progress is not met for a reason that I will explain in this simple scenario. Okay? Assume that we have two threads, 0 and 1. These threads, basically, they are executing critical and non-critical sections. However, as we mentioned before, there is no relation, no correlation between the length of times of critical and non-critical section within a thread or compared to other threads. Random, the length of the critical and non-critical section. Correct? Now, if we look at this thread 0, we will find that it has various segments of code to execute. Some of it critical section, others are non-critical sections. For example, it has this length of first critical section, and then this length of non-critical section, and then another length for a second critical section, and so on. Similarly, T1 has also variable length of critical and non-critical sections. Okay? Now, the execution. Let's assume initially the one who started to execute what? Thread 0. And at the very beginning, we have turn set as what? 0. That's in the initialization of the lock. Correct? Now, if thread 0, when it starts executing, okay, it is executing a critical section, which means it should call a method of the lock which is entering critical section. Right? And that method receives the ID of the thread. Right? So 0. Now 0 sent to the method. The method, what does it do? It compares the ID of the thread with the value of turn. If they match, then the method returns, means granted to continue. Entering critical section. If it did not return, then not granted, right? So, okay, now I can go faster. Okay, so thread 0, ID 0, entering critical section. The ID and the turn are equal, means the method will return. Thread granted to enter critical section. Thread T0 will stay in its critical section for the length of that, until this point. And then it will proceed to execute what? Its non-critical section. Right? Up to this point. Won't be able to finish all of the non-critical section, up to this point. Now, at the time of leaving the critical section, thread 0 must call what? Leaving critical section. And leaving critical section will change turn to what? To 1. So this is the result of leaving critical section. Now, if you see these dotted lines, blue lines, okay, they represent context switching. Context is switching. So assume that each one of them here got a particular amount of time for the time slice, okay, say equal. So now at this point, we have context switch, thread 0, okay, being suspended. Now who will start? Thread 1. Thread 1 started executing, and it's executing critical section. Right? The very first thing is critical section for thread 1. So we'll start the executing of it here. But before it starts executing of it, it should call a method which is what? Entering critical section. For which we have to compare the value of turn, which is currently 1, with the ID of the thread 1. They're equal. Right? Then the method returns means thread 1 granted to enter critical section. So we'll be executing critical section up to this point, which is basically the end of the critical section for thread 1. And then should call the method which is leaving critical section. Leaving critical section does a very simple thing. Change the turn to be what? 0. It was 1, now change it to what? 0. To give opportunity for the others to run. And then thread 1 continues now, because it still have this amount of time to use in its time slice, right? So it will continue to execute the rest of its code, which is a very small amount of time for a non-critical section. So it's going to execute it. And for that, it does not need to obtain a lock, right? And then once finished the non-critical section, at this point, it will enter its second critical section. Right? So at this point, trying to enter its second critical section, it's supposed to call the method which is what? Entering critical section. That will does the comparison between the ID of the currently active thread, that's 1, with what? With the value of turn. And what's the value of turn? 0. They don't match. So what do we have here? This thread has been given this amount of time to execute, this time slice. Okay? It wants to execute a critical section at this point. No other thread is in its critical section. However, this thread who's active was not allowed to enter its critical section. Okay? So progress is not met. Okay? So we have seen here a scenario in which the thread can block itself, okay, from entering what? Consecutive critical sections within the time slice that had been given to it. Okay? Okay, so do we understand this? Okay, progress is not met in this case. Now, a second implementation. The second implementation says that we're going to use something different, okay? Basically, flags. Flags to implement the intention of entering critical section. Okay? Because we had the previous problem there. I have given the turn to another thread to enter its critical section as a working, currently active thread. Okay? Give the turn to other thread entering critical section. But that thread at that time even is not active. Right? Or maybe might not need to enter its critical section. Right? So here, we will base the the logic of entering critical section on the intention of entering critical section. So each one of the threads will have a flag. This flag is raised up if the thread is willing to enter a critical section. Is willing to enter critical section. But at the same time also we want these threads to be nice to each other. Okay? So that they don't block each other. So a thread willing to enter its critical section, the very first thing that it's supposed to do is to raise up its flag by setting it to what? To true. So if the one who's calling this method is thread 0, then flag 0 should be true. Or if the one who's calling this method is thread 1, then flag 1 should be true. So I'll be having a number of flags equals to the number of active threads. Right? But we said we start small scale. Now, thread 0 willing to enter the critical section sets the flag to true and then checks the flag of the other thread. Okay? While the other thread is willing to enter its critical section, I'll suspend myself. Okay? Means being nice to the other thread, giving chance to the other thread to enter its critical section. Okay? I won't block. Right? Why? Because whoever entering the critical section once leaving, what would it do? Set its flag to false. And that will change what? The condition in the while loop. In the condition in the while loop. So if a thread had been suspended because of this condition is true, okay, later on when this thread is awakened again, right? Restarted again at this point, okay, resumed, not restarted, resumed at this point, the condition is checked again. And that might become false, right? Because of leaving critical section. Now, for this one and only one can be active at the same time. Because this can be active, a thread can be active in a critical section only if it has the intention of entering critical section and the other doesn't have. Right? Only that way. And we have only two threads, so mutual exclusion is what is met. Now the other condition, progress, is met or not. What do you think? Here, the idea, the worker is not blocking others, right? But let's look at this scenario through this code. Assume that thread 0 is willing to enter its critical section. Okay? Means gonna call this method with t equals to 0, and it will set its flag to true. Right? So thread 0 has intention to enter critical section, and the flag is true. It's flag. Now, when executing the code flag 1 equals to true, okay? Or before that, just before that, there was a context switch. We can have, right? So at this point, we have a context switch. Flag 0 is what? True. Flag 1, we don't know yet, okay? Now, let's resume another thread, which is thread 1 in this case, right? Because thread 0 is suspended as a result of context switch. Now, thread 1, assume it's willing to enter a critical section, one of the scenarios. Now, it will set its flag to true, right? And then try to proceed to the loop. The loop says, while flag 0 true, which is true, right? Flag 0 has the intention, what? Suspend yourself. So now thread 1 suspended as a result of what? Thread 1 willing or has the intention to the critical section. That's good for thread 0, because now thread 0 can resume. However, when thread 0 resumes back, it will resume at this point, right? We'll enter the loop, check the condition. Flag 1 true? Yes. Suspend yourself. Okay? And this will continue. So what do we have? Two nice to each other, right? None of them obtaining the lock, right? This is a deadlock situation. None of them is basically proceeding, okay? So progress is not met because of this one scenario. One counterexample is enough for you to say that progress is not met. Now, the other idea, which is the third attempt, is, by the way, successful attempt, is called Peterson's algorithm, okay? And it uses the ideas of the very first two attempts, turn as well as flags, okay? So we're going to use the turn, same turn concept, and the flags concept. But the logic now will be this. So we had a problem first. We tried to solve it. We've been too nice in solving it, so things didn't work. Now, the idea is like that. A thread willing to enter a critical section, it will set its flag to true. Okay, this is for thread 0, as same for thread 1 as well. This is duplicate of the code, which shouldn't be if we have multiple threads. Later on, we can manage that. But it will set its flag to true, and then it checks two conditions. Two conditions, okay? Both should be true for it to suspend itself. If any one of them false, then it will be granted to enter a critical section, right? The two conditions are, is the other thread having the intention to enter a critical section? Now, this condition by itself won't work, and we have seen why, right? And the other condition, is it now the turn for the other thread to enter a critical section? Okay. Is it now the turn for the other thread to enter its critical section? Now, if you put the first condition, it has the problem of the second algorithm. Okay, and if you put the second condition only, it has the problem with the first algorithm. But if you put the two together, okay, each will solve the problem of the other. So the idea is that you give chance to other threads, okay, but at the same time, okay, we are not implementing alternation as implemented in the first algorithm. The first algorithm, the idea is alternation, okay? The access of critical section done for thread 0, then thread 1, then thread 0, then thread 1, alternation, okay? And that caused the problem. Here, no, alternation and the intention to, okay? And the intention to enter the critical section. So we go through this code, have a context switch anywhere, okay? For one scenario that you want, okay? You won't have, okay, any counterexample that goes against the logic, okay, of progress. Against the logic of progress. The very first one, which is basically mutual exclusion, is met even by the first two attempts with the and here definitely is met as well. Now the bounded weight, as we said before, it's an implementation of fairness within the algorithm. Okay? Is this clear? The third algorithm? Any question about it? Any question? Okay. So now we proceed to other ways of implementing the lock. And we said one way to do so is by using atomic instructions that are available by the hardware. Okay? So hardware, assuming that it has atomic instructions, implementing the logic of get, set, get and set, and swap instructions. What does it mean, atomic instruction? What do you mean by saying the instruction is atomic? Means interrupt are disabled, okay, during the execution of the code for that instruction. So it is executed as one unit, okay? One unit. No interrupts, no context switching, okay? Which is the timer interrupt, right? Nothing, okay? No interrupts. So if the instruction started, it will remain until it's finished, okay? So if I say swap is an atomic instruction, then I can't assume that there was an interrupt, okay, during the execution of swap, right? Now, if we assume so, of course, each hardware itself, it has its own, okay, format of these instructions. So now let's say that, let's model the hardware who supports these instructions by a class in Java. Say that the class name is hardware, okay? So hardware has atomic instructions, and these are get, set, get and set, and swap. Supports these as methods, right? Which in hardware as instructions. Then, can we write a code of a worker, where we do the guarding, okay? We guard, okay, the execution of critical section, because the worker will be executing critical and non-critical section. So can we put some kind of logic before executing critical section that takes advantage of these atomic instructions, or no? Okay. First of all, let's look at how they work. The get, basically, it returns the value that is saved in a Boolean variable. Boolean variable. So in this case, I used it, Boolean variable. Now, this Boolean variable, 0 or 1, that's good. That implements the concept of what? Locked and unlocked. Available, not available if you want to, right? And so I can think of it that way. Value is the lock, okay? And the value inside it, okay, it's saved in it, which is either true or false, will tell me whether it is locked or not locked, okay? So initially, we set the value to false, means it's not locked. So false means what? Available, not locked. Okay? Not locked. That's the status or the state of the lock itself. Now, get, it will return the status. Set, it will set the value. Means you can use it to lock and unlock, depending on what you send to it. If you send true, then you lock it. If you send false, you unlock it, right? To this one, to this method set. Now, get and set. Get and set is a method that receives either true or false, right? A Boolean. Now, it will save the value of this variable value, what's saved in it. It will save it and return it to whoever called get and set, right? Right? So this is the return value of get and set, which is the current value of the lock. And then change that, so overwrite it with the new value passed to the method. New value. Right? So first I get the old value, and then I set the new value. Clear? Now, swap. Swap, it works by having two objects of this class, two looks. When I say swap them, okay, If both of them are true, they remain the same. Both the false remain the same. If one false, the other true, become the other way around. Right? Clear? And all of these are what? Assumption, atomic methods. Well, atomic instructions, but here Java, atomic methods. Of course, they are not in this case, right? This is just a method in Java, and an interrupt can happen anywhere, right? I mean, context switch even can happen anywhere while executing it. But we assume so, right? However, if we really want these methods to be what? Safe methods, okay, then we can do so. And I think later we will talk about that when we talk about synchronization with Java. The very first thing that we should start with is by using synchronized keyword, if you remember, right? Then we need to add something else as well. Right. So now, this is a portion of the code for a worker. A worker. Worker basically will be doing continuously one of two things: executing a critical section and executing non-critical section, which is the remainder section, continuously. Right? Right? Okay. Now, we need a code before entering critical section, okay, that implements the logic of getting the lock. Getting the lock, or looking. Right? Okay. We can do that by using the get and set method. Get and set method. Of course, every one of the workers, the cooperative workers, will receive one object, and that object is of type hardware, right? Which has value implementing the lock, and the methods that you can use on value. Correct? Right. Now, to get the lock, you can use the method lock.get and set true. Get and set true. So if you send true to the lock, what will happen? You will get the old value of it, what was it initially, and you will set it to true, because you will get into the safe, and the safe is locked once you are in the critical section, so that others cannot get in. Right? Okay. So it will return the initial value of the lock, and will set it to what? Locked. If the initial value was false, means it was available, right? And you set it to true, means what? You obtained the lock. And what is returned to you is false, right? Because it was available, the initial value. So if it returns false, then you are out of the loop. Out of? And if you are out of the loop, means you are granted to enter. The lock was available, and you managed to get it, and you look it, and you are already in critical section. But if the lock value was true, means currently is used, okay, by another thread, and you use get and set, what will happen? It will return the initial value of the lock, which is true, right? And it will set it to what? A true. But when it returns the true, you're still in the while loop. You will get into the body of the while loop. And what does it say there? What does it say there? Yield. Suspend yourself. Okay? You've been trying to obtain the lock, but you couldn't, because it's already locked. The value is already true. And that will result in getting into the loop and then suspending the calling thread. Clear? So this is a good logic for what? For entering critical section. Now, on the other hand, leaving the critical section. If a thread is leaving critical section, then it should set the lock to be free, available. And that is by setting the value to what? False. Setting it to false. So set is only called for a thread. In your code, is only set for a thread that has the lock. But if you use it with a thread that you are not sure whether it has the lock or no, then the whole implementation, okay, the logic of your implementation is totally wrong. Right? And then we have the other code, which is the remainder code, That's the non-critical section, and then the cycle is repeated again. Each time a thread is willing to enter critical section, we'll do this. So here we have implemented, okay, the logic of entering critical section using the atomic instruction get and set. Clear? How does it work? Any question? Good. Another implementation. The other implementation is by using another instruction, which is basically the swap instruction. Swap instruction. Again, the logic of the worker doing critical section and then non-critical section. Before the critical section, we need a logic of obtaining the lock. After that, a logic of the releasing the lock. Releasing the lock is always the same logic, setting to false, but entering. Okay, entering the lock. Each one of the workers who are cooperative workers, they will receive an object of what? Hardware class, right? Which is basically a value, that is the lock status, okay, state, right? And a number of methods that we can use on. Correct? So we have an object already coming from where? To the constructor of the worker, which is the lock object. Okay? So this one in the main application, we create this lock object and we send it to the worker. Now, the worker will use swap. Will use what? Swap instruction. But you can't swap. If you want to use swap, then you should have another object of hardware, because we're swapping two hardware objects. The swap instruction receives an object of hardware. So fine. I have already the shared key of type hardware passed to all the what? Cooperative workers. And now locally each worker creates an object of hardware with the intention to what? To obtain the lock. With the intention to obtain the lock. So here, locally, this worker defined a hardware object and passed it through to the constructor of it, means the value is true, right? Value is true. That object name is key. Is key. Key why? Well, you can't even quote anything, because actually you're gonna use it to swap with the lock. So it's your mechanism of looking and unlocking the object, right? Unlocking the lock in this case, right? Now, what we need to do is continuously, while we're trialing, okay, because it might not work for the first time to try, trying to get the lock, right? And then continuously, we need to make sure that our intention is set to true in the key that we are using to swap. Okay, so that's why we have what? Key.set true. Even though at the very beginning we initialized it here, okay, the time we created it has true, but it might change now. Okay? And now, continuously we try to obtain the lock by using swap. Swap is a method of hardware. I can use it with a hardware object. That's lock. Lock.swap key. Now what would this do? It will swap the values in the two objects, lock and key. Key is true. The value in there is what? True always. Okay? But after the swap, the value of the key will be the value that was in the lock. Right? So if that value is false, means it was free and I managed to what? To access it. But if that value is true, means it was not free. I swapped true with true, I got true, means it was not free, means I did not manage to access it. So that's why here we keep repeating this as long as the value that we retrieved after the swapping, which is currently in key, right, is true, then keep trying. Keep what? Keep trying. Clear? Is it clear here? So if it was available, what you will get after the swap, the value in key is false. false, we will go out of the while loop, and then you enter the critical section. The calling thread can enter the critical section. So this is the logic of using what? Swap, atomic instruction to implement looking mechanism. Clear? Okay. Now next, we move to the what's commonly used, okay, in synchronization. So all of what you've seen, okay, the aim of it, as I mentioned before, critical section and showing, well, critical thinking, in fact, using thinking of critical and non-critical sections, right? We need to have some critical thinking in there and show you different alternative ways of doing things. That's all. But in practice, you will be using high-level languages support for synchronization, as well as operating system support for what? Synchronization. Right? So you can consider what we've been explaining so far as motivation to the course, motivation to the topic, let me say. Now, support for synchronization by high-level languages, we choose Java, okay, to demonstrate that kind of support. But similarly, C++, C, C#, and so other languages as well, okay, they have their own support for synchronization, okay? If you remember the time we introduced the account, okay, or the bank system, okay, application, where we have an account that is shared by multiple threads. The time we talked about multi-threading, do you remember? And we've been trying to demonstrate the inconsistent view of the balance in the account object because it had been accessed by multiple threads simultaneously, right? And we have seen a similar thing also in the producer-consumer problem. Did we? Yes? We have seen the bounded buffer accessed by the producer and the consumer and the inconsistency that might happen. We said in Java, okay, we can use the synchronize keyword, right? And that will do what? We already used it, in fact. That does what? It activates the lock of the object. Activates the lock of a Java object, which means every Java object by default comes with a lock. Okay. Now, to activate that, then synchronize should be used. Synchronize can be used on the whole object, or it can be used on a method within an object, and it can be used on a segment of code, okay, within a method in an object, okay? And in all of these cases, what would it do? It will activate, one of the things that it does, activate the lock of that object, okay? Activate the lock of that object. Now, we also mentioned when a synchronized method is invoked already by a thread executing a synchronized method, then no other thread can execute any synchronized method of an object. So if they have requests to execute synchronized methods of that same object, while one is already executing one of these synchronized methods, then all of their requests, those who are requesting to execute synchronized methods, all of their requests will be what? Buffered. Will be what? Buffered on that object. So every object has an entry set, okay, that will hold requests to execute synchronized code of the object. Synchronized code of this object. One of them there. Now, what about other threads who have requests to execute non-synchronized code of this object? Do they have to queue here? They don't have to, because we said non-synchronized method can be granted access, no problem with that, even if there is a synchronized method, okay, active, okay, not yet finished with its code, right? So that's the idea. You can use it this way. For example, you could use synchronize on the whole object, or you can use synchronize on the body of the whole method. For example, this is a method within an object, and then the very first thing you write in that method, synchronize this, okay, and then you have what? the code of the method. This was the only way to use synchronization on a method last time. And then we could use it as simply as this. Just have synchronized before the method name, and that will make the code of the method what? Synchronize, okay? Right. So these two are what? Equivalent. These two representations are equivalent. You synchronize the body, or you synchronize basically at the declaration of the method, or let me say the signature of the method, then both are the same. Now, properties of this. No thread can get lock on the object X while X is executing what? While a synchronized method is executed within X, okay? And then the locked code is what? Is the synchronized code. Means if other threads are trying to access code that is not synchronized, they are what? Granted. So they're looking only for the synchronized code. Now, the synchronized or the looking will be the looking of the segment that has synchronized, okay, will be freed, okay, will be unlocked when what? When that block terminates. But the termination could be reaching the end of the method or the end of the segment, let me say, because it could be only a portion of the method. Or if we have a return, continue or break, or we have an exception thrown by the method. So any one of these reasons will release the lock. So synchronized, it ensures mutual exclusion. Not only one thread executing a code that we think is critical. That's why we have it synchronized. Okay? However, it does not ensure other things that can be as a result of using synchronized. Okay? So the consequences of using just synchronized can lead to a problem which we call deadlock problem, in which a thread might block the rest of the threads and itself, so none is progressing. None is progressing. Which means if I am to solve a problem using Java synchronization, it doesn't mean it's synchronized keyword and I'm done. There is a lot more to be done. Okay? So that's basically what we have here just at the very beginning. I mean, just trying to introduce what synchronization with Java is. Next class, I will repeat some of this for 2 minutes, and then hopefully we finish Java synchronization in 1 hour. Okay?